capacitor of choice when we're making products that have to have high reliability, like servers and routers and that kind of thing that are used in the internet. The advantage of both the organic and standard tantalum capacitors is that they don't come up in very high voltage ratings. If we need something with a high voltage rating, we wind up using aluminum electrolytics, which will extend voltages up to a couple of hundred volts. They're less expensive than tantalum, either tantalum. Where you'll see these parts used is where we have a very low cost design. The switching supplies for a PC almost always have this kind of bulk capacitor in them. Part of what one has to do when engineering a power subsystem is to determine what the inductance of mounting the capacitor is, so we can include that in the model. So we don't wind up being fooled about what we really have. This is a test board. It's made out of a section of a 26-layer board, and it has 5 power plane pairs in it, being 1, 2, 3, 4, and 5. And on the left-hand side, we've got access points, one to inject a constant current, the other to measure a voltage. And that's how we're going to measure Z versus F of capacitors. Near the left side of this test board, we have that X2Y capacitor that was advertised as being somehow magical. The 8-leaded IDC capacitor, 0402s, 0603s, and so on, of different package sizes, connected to each of the 5 plane pairs. What I'm going to show you as in the next few slides is what the inductance versus frequency is if we connect our capacitor to the first pair of planes below the surface, which is the very best we will get because the length of the inductance is as short as we can make it. And then we'll have the same capacitor connected to the bottom pair of planes to see what that looks like. This is a cross-section of that test board where we have on the left-hand side, the red capacitor is hooked to the first 2 planes, V1 and its ground, and on the right-hand side, hooked to the bottom one, V5 and its ground. And so we're going to be able to see for the same kind of capacitor what difference it makes to mount to the plane nearest the surface as opposed to near the bottom of the board. I've touched on this already, but we'll elaborate right now. For us to use a capacitor in a PDS, we've got to connect it to the planes that contain the right power rails. The same is true for the IC package itself. The mounting structures add inductance whether we like it or not. They're mounting pads, and then the V is required to go down into the appropriate layer of the board. You'll see some measurements coming up that for the best capacitor mounting you can do, the mounting inductance dominates the picture. So we will, once we know this, we won't pick a capacitor package because of its inductance, but rather because of its cost or availability. These are some of the measurements we made for several different packages, and in these measurements are connecting to the first 2 layers below the surface, meaning